Okay, so yeah, so I mean, the kind of my personal take on motivation on this type of project is that, you know, when you look at many body, you know, to kind of see, look at the results on many body dynamics of interacting many body systems, you know, I mean, in a particular, this conference is on chaos. So if you compare what with the situation on, let's say, classical chaotic dynamics of single particle models, like, you know, there you have kind of models which you can solve, you know, in the class for students, like in 20 minutes, the so-called cat maps or Baker maps, right? I mean, they're very simple dynamical systems for which you can prove decay of correlations, so-called dynamical mixing or ergodic properties, and so on. I was really missing that kind of models for many body physics. So, I mean, you know, we have 3 models, which are kind of quite trivial from this point of view. And then we have basically interacting models, integrable models, which are very particular, which are fine-tuned. And then non-integrable interacting models are basically, you know, they are non-tractable, right? So the question is, are there tractable models of that sort? And that's exactly what my talk is about. These are the so-called dual unitary circuits. And I explain you why these models are tractable, actually. So they can be mapped to zero-dimensional dynamics of an open quantum system. Yeah. And okay, so let me just give you a brief definition of the models that I'm going to talk about. So just imagine, I mean, I will talk about Floquet circuits, as was already motivated by John Chalker. So I will have no Hamiltonians around. I will just have unitary evolutions, discrete time unitary evolutions, which you could think of as periodically driven dynamics or just discrete time dynamics. Yeah. So, and these evolutions will be kind of generated by two-qubit gates, if you want, or two-body scattering matrices, which take 2 states I and J and produce 2 states K and L. Yeah. So you can just think of this as a unitary, which which acts on a p-squared dimensional theta space, right? But now what I will do is I will also consider not only this unitary, but I will also consider this guy, which I will ask to be unitary, which means I will consider the so-called reshuffled quantum gate, which I will denote as util there, where this where 2 of the states will be reshuffled, so that the ins will be I and K, and the outs will be J and L. And I will tell you that some magic happens. I will try to explain it to you. There is some magic when you require that not only U is unitary, but also util. Now, in terms of diagrams, because it's kind of nice to plot pictures and, you know, to avoid derivations, right, which are difficult to understand, it's better maybe to plot pictures. So, you know, everything that I will do, everything that I will present to you basically can be understood just by looking at pictures. So, and the fundamental diagrams which I use basically are the so-called what we call fusion diagrams, which means that when you contract U and U dagger, obviously because of unitarity, these 2 guys contract to 3 lines, right? This is the unit operator. Now time for me runs always vertically. And then when you contract them sideways, this will be the dual unitarity. Then also these guys can be contracted to empty lines. Yeah? This I will call sometimes dual fusion rules or space rules. And then, okay, and then let me now go from gates to circuits. So then what I will use a lot in my talk will be this type of quantum circuit, which I will on purpose draw in a slightly unconventional way. At least when we started drawing those, they looked a little bit unconventional because people usually draw brickwork circuits with vertical lines. But here we basically draw them with 45-degree angle lines, simply because you can just turn your head around and you look at this circuit as a circuit which propagates left to right, which basically looks completely symmetric. So, I mean, you can think of this as a kind of standard brickwork circuit, which I will now denote as W, this double stroke U. And then, you know, you can just think of this. This is a forward circuit of a system of size L, where L is here equal to 6 and times 10 2. But you can also think of it as a circuit propagated by util of a system of size 2 for 6 time steps, right? And there is clearly a duality of traces. I mean, you could write now a trace of the propagator as a partition function of this StatMech vertex model, where these gates would be just like now a vertex, complex weight vertices if you want. And clearly, these two things are identical, which means that this partition function can be just computed using the row transform matrix, which would be the standard evolution, or a column transform matrix, which would be the dual evolution. Now, the question is, what happens if the dual evolution is unitary, right? I mean, obviously, this is topology. I mean, you can do this for any circuit. The question is, what does it buy to you if you ask the tilde to be unitary? Oops, what happened? Yeah. Okay, so now, I mean, I will not go through any of the technical details, but after all, I have just 30 minutes, but just let me advocate immediately. I mean, this was very fruitful since it allowed us, I mean, this is unitarity of dual evolution, since it allowed us to prove random matrix spectral form factor for Kick-Teasing model in 2018. And I also have to stress that this concept of space-time duality was used before by a group of Thomas Gurry, in fact, by Boris Gutkin and company. So they basically discovered this space-time duality for Kick-Teasing model. And then also I should mention the work by Austin Lamacraft and Sarang Gopalakrishnan, who also translated Kick-Teasing model to dual unitary circuits. So, okay, so let me just give you 2 slides on spectral form factors. I mean, they were also kind of discussed in the John Chocker's talk. So I've tried to now present to you a state-of-the-art result on, let's say, a rigorous connection of spectral form factors to random matrix theory. And of course, there are caveats when one makes claims like that. I will come to that. Let me just give you a brief definition of spectral form factor. So this is, I mean, just imagine that your spectrum is a gas. So now you take a kind of your unitary evolution, which is U. So there is the this is the Floquet propagator or a generator of your dynamics, which is a one period of time propagator U. And the spectrum of U is a set of points on unit circle, which you call quasi-energy spectrum. And this can be thought of as a gas confined on a unit circle. So it cannot expand, it's confined. And this gas has some statistical mechanical correlation functions, right? And you just imagine the simplest non-trivial correlation function, which is the 2-point function. So imagine that this gas is uniform. So the 1-point function is trivial, it's just the density, and density is by assumption uniform. So then you define a 2-point function, which is the density correlator integrated over the circle. And the Fourier transform of this 2-point function of the spectrum is a spectral form factor. So again, it has a very simple expression in terms of the propagator. I mean, this is just a 2-line straightforward calculation, but this is what we have seen in John Chocker's talk. I mean, spectral form factor is, if you want by definition, trace of u to the t squared, trace of u to the t modulo squared, right? And of course, one has to be careful here. I mean, the spectral form factor is not a self-averaging quantity, so it doesn't make much sense unless you do some averaging. So that's why we have to do some averaging, either over some disorder or some parameters of the model, or even some moving time averages are enough. Okay, now what does random matrix theory tell us about spectral form factor? I mean, there are closed form results. For example, for systems without time reversal, the spectral form factor starts with a linear ramp. For Floquet systems, there is no decay because still thing starts at time equal to 1. So time equal to 1 is already where a ramp starts in the random matrix theory. So the only thing you have to be careful, have to pay attention here is the slope of the ramp. So when there is no time reversal, the slope is 1. When there's time reversal, the slope is 2. And this is all when the time is much shorter than the ultimate time scale where things saturate, which is the Heisenberg time. So for time is much shorter than the Heisenberg time, and we will be only interested in thermodynamic limit because that's the only rigorous type of calculations which we can do. So we can only address the ramp, but not the approach to Heisenberg time. But again, there is an interesting time scale which was also discussed by John, which is the tau-less time. So, I mean, the question is, I mean, can we understand the behavior of tau-less time for particular class of dynamical models? How does this depend on system size? How does this depend on system parameters and so on? And the models that we're going to discuss, these dual unitary circuits, they have a very nice and very particular property, which is that there is no tau-less time. The tau-less time basically is 1 or 0. Then that means that these models could be thought of as critical chaotic models, which means scale-free or models which have no time scale. Well, in thermodynamic limit, yeah. So otherwise there is the Heisenberg time, of course. Okay, so now let me just give you the state-of-the-art kind of result on the spectral form factor. And I will not give you any details of the proof, but let me just give you one slide, one line of calculation, which is basically explaining to you why this unitarity of the dual evolution is so important. So the spectral form factor, I mean, I will now consider a general class of Floquet circuits, which will be like this. So there will be two half layers of bricks. So there will be the bricks and the other bricks, there will be bricks in the different, I will assume for simplicity that all the bricks are the same. But then I will insert some tiny one bit unitaries, which I will assume that they are distributed over SU2 with some measure. So now the point is that, of course, I don't want. Yes, question?
Was a problem in your audio? Sorry to interrupt, Thomas. There was a problem in your audio. I think multiple in your mic. I think now it's good. Maybe you can.
Is it too weak or?
It was a little bit.
Is okay now?
Disturbed, but now it's okay. So.
Okay. So let me try to continue. Yeah? Let me know if it doesn't work. Okay. So now. So the point is, okay, this is kind of the generic, let's say, a model, which is quite general in the sense, which of course have dual unitary. And then I allow any arrangement of single qubit gate or qubit, if you want. This could be any, it doesn't have to be qubits, it can be qubits, but I will just state results for qubits in order not to make it too complicated. So the point is that this single qubit gate can be arbitrary. The only restriction is that they have to be ID distributed with smooth distribution over the corresponding, if you want, a unitary group. So U2 or SU2. And the statement is the following. So in that case, the disordered average spectral form factor in thermodynamic limit is given by the dimension of the cumulant of a set of operators, which is given by magnetizations in time direction and interactions in time direction, which are translation invariant. Translation invariant in time. So now you ask about commutant. You ask about the maximal set of all operators which simultaneously commute with all these guys. And of course, you immediately guess a set of operators, which are the translations, right? But you know how many translations you have. There are T translations. So the only thing you have to prove is that there are no other operators. So that the cyclic group of T translations is the maximal set which simultaneously commute with these operators. So it's a kind of a very nice problem or a clean problem in algebra, if you want, in operator algebra, which you can handle and can solve. And this has been done in a paper with Bruno and Pavel a couple of months ago. And this, as I said, this can be generalized to various aspects. It can be generalized to qubits, so to dual unitary qubit circuits. Of course, we don't know large classes of dual unitary qubit circuits, so we take those which were recently discovered by Austin and Place, I think. Also, we can take arbitrary modulation of bricks. You don't have to have constant bricks, but you can have arbitrary modulation of bricks as long as bricks are sufficiently far away from the swaps. I mean, swaps are the nuisance, right? Because swaps will make your, swaps will make your dynamics non-interacting. So swap circuits will not be chaotic, even if you take unitary Scramble scale. Okay, so. Please interact me with questions if there is anything. So because maybe it's better if I. Okay, so now this would be this would be all I wanted to say about spectral form factors. But let me now spend the rest of my talk about something much simpler, which are the 2-point correlation functions. So I mean, these are the simplest objects which you can think of calculating for these circuits. So let's just think of calculating 2-point functions, which are arbitrary 2-point functions in space and time. So imagine you have now this circuit, which you can think of as a forward-backward circuit, right? So you take a Heisenberg picture of an operator, you compose it with U to the T and U to the T dagger, and then you contract it with another operator placed somewhere else and take a trace. So this would be like an infinite temperature correlation function for arbitrary operator, which is local. So what I have in mind now are local operators, and arbitrary spatial points X and Y, and arbitrary duration T. The only thing I require now is the thermodynamic limit again. So I require that the system is large enough so that the boundaries will never kind of hit me, right? So that's a requirement. But for these models, thermodynamic limit is is reached at finite system size, which is of the order of 2t. So now, okay, so now, right. So what I want to do now is to contract. Now this circuit is basically, again, it's a vertex-like model, right, of 2D partition function type object, which is inhomogeneous, meaning that half of the weights are different than the other half. But you should imagine that you have periodic boundaries in space and in time. So now this guy has, okay, so now again, as I have some problem with my computer, seems it's getting very slow. Okay, no, yeah, some delay. Sorry. So now, again, I could just prove to you this simple result, which says that the only correlation function, that the correlation function is non-vanishing only when the spatial displacement is exactly equal to plus minus t. And then it is given by, it is given by this diagram. So for that, I could use these two diagrams that I have shown you in my first slide, this forward and dual fusion rules. And I could show you that unless x minus y is equal to t, all these diagrams will result will vanish, right? And I will not show you that because it would be still taking too much time, but I could just give you intuitive reason why it should be so. And the reason is the following: since I have the dual unitary dynamics, now imagine I have unitary brickwork circuit. Unitary brickwork circuits has exact light cone, and all the quantum correlations are confined within temporal light cone, which means are here. But now I have also dual unitary dynamics, which means I have also spatial light cone, and all the correlations should be confined in the space cone. So the only non-vanishing, I mean, the only geometric place where correlations can spread is the intersection of these two light cones, which is the two light rays, which spread at velocity plus minus 1. So that explains why the only correlation function, the only non-vanishing correlator is at x minus y equal plus minus t. And then it is given, as I say, it is given by this diagram, but this diagram just tells, this just, is just again, a diagram for iteration of a completely positive trace preserving map on a single qubit. You can imagine you have a qubit sitting here in a state A beta. I mean, operator can be also thought of as density operator. And then you propagate it by 1 time step, 2 time step, and so on by a CPTP, which has this diagram, right? Which is just given in terms of this expression. So now the correlation function can be just, computed at the end just by diagonalizing this single qubit CPTP, right? Which that has a spectrum inside unit disk. So imagine that it has some eigenvalues, lambda plus or lambda minus indexed by gamma. And so then, you have the spectral decomposition of this CPTP, and the correlator is just a finite sum over these exponents, which are the eigenvalues, right? And now, depending on the spectrum, you can have various behaviors. You can have a non-ergodic behavior for when all the eigenvalues are equal to 1, which is only happening for swaps. You can have behavior which is non-ergodic but non-integrable, meaning that there is some non-trivial eigenvalue. There is always an eigenvalue 1 which corresponds to unit operator, but that we have excluded because we are looking at the traceless, correlators among traceless operators. So, I mean, imagine that there is a non-trivial eigenvalue 1 that corresponds to, that would signal that you have a non-ergodic dynamics, even though it could be non-integrable in general. Then if there is an eigenvalue which is on unit circle, but not at 1, then the corresponding eigenmode would provide persistent oscillations. It should be termed time crystal, for example. And if all non-trivial eigenvalues are in unit disk, then you would have ergodic and mixing behavior. So all the correlation functions, all the local operators decay exponentially. Okay. Now, there is an interesting problem of characterizing the set of dual unitaries. I mean, you may imagine that this is a fine-tuned set, so that maybe it's very particular, but really it's getting super slow for some reason. But it turns out that this set is not as small as you might be afraid of. It turns out it is just codimension 2 submanifold of SU4 or U4. So of all possible interactions among two qubits. So you can take this general representation of SU4 or U4 in terms of two SU2s on the left, Heisenberg gate, and two SU2s on the right. And a dual unitarity just forces you 2 out of 3 parameters in the Heisenberg gate to be pi over 4. And all the other parameters are put in general. And then among those gates, you have swaps, you have integrable gates, which are, let's say, the Heisenberg XXZ, trotterized integrable Heisenberg XXZ circuit, or you can have also self-dual Kick-Teasing model. Okay. Here I want to point out that there has been recently some progress on generalizing parameterization of dual unitary circuits to qubits. And also there has been a generalization of the concept of Kick-Teasing model to higher dimensional local Hilbert spaces. Okay, so there is, maybe I probably have to skip that because I'm not sure how I'm doing with time. Andrea, how much time do I have?
So I would say 10 minutes.
Okay. So yeah, so now probably I had prepared some speculative slides on spectral form factor in generic circuits, which are not dual unitary, but if you want perturbed dual unitary. I mean, decay of let's say spectral Lyapunov exponents, but you know, it's I'm just looking at my results. Of course, you cannot conclude. So, question is, can you make some bounds which would at least bound away some ergodic pieces of parameter space away from localization, for example? But it's hard, and so we don't have really any results. So I don't just want to take speculation here. I also want to stress that there will be to beyond dual unitarity. So to make interesting connections between non-unitary evolutions and corresponding dual unitary evolutions. And right. But let me just go back to our work. So, for example, what one can do using dual unitarity, strict dual unitarity, one can make some precise observations of operator spreading and operator entanglement. For example, in this paper with Bruno and Powell, we were able to compute the rate of growth of NE2 entropy using 4 copies of the circuits. And this result is not totally rigorous, so we have to we rely on some conjecture, which seems to be perfectly satisfied. But modulo the conjecture, we have analytic results on the growth of entanglement as a function of the key parameter in the parameterization of dual unitaries, which is just Heisenberg J parameter. So you remember, in the Heisenberg gate parameterization, 2 out of 3 parameters have to be pi over 4, but the third could be anything from 0 to pi over 4 in principle, and pi over 2 essentially, right? No, pi over 4, yeah. So it seems there is some interesting phase transition. So for small j, we have a maximal growth of entanglement, which is log 2, which is twice larger than the growth of entanglement for high random circuits, if you want. And then there is a discontinuous decay of the growth rate with increasing j down to 0 at swaps. Then, before I go to perturbed dual unitary circuits, let me just advertise most recent work of mine, which formulates dual unitaries in the also IRF language. So, I mean, if you are getting bored with brickwork circuits, as I also a little bit, I mean, you might wonder whether there exist other paradigms which are dual unitary, which are also kind of simple to treat within StatMech tools. And these are the IRF models. So imagine what could be an RF model. I mean, this would be a model which is connected to gates which are 3-bit gates or 3-qubit gates which act non-trivially on a single qubit. but they have controls on the two adjacent qubits. Now, if you have such a circuit, so 3-qubit circuit, then this can be immediately mapped to an IRF model where this 3-qubit gate, which is again control on two edge qubits, which means it doesn't change the edge bits, but only can change the middle bit depending on the states of the two edge bits. Now, this is exactly, this can be exactly identified as a plaquette, which depends on these 4 integers, right? And this is the sort of IRF interaction around the phase. Now, this is not a stochastic, or that is not a statistical IRF model. It's a unitary IRF model. And what one can do immediately is one can define dual unitary IRF models. First, one does the standard operator folding. So, writing correlation functions in terms of evolutions of, in terms of Heisenberg gates. These so-called folded gates, which are just tensor product of two state gates, if you want. So this is what we did, what we can do for brickwork gates, and this is what we can do for IRF gates. Again, the operator IRF gate is again an IRF model, and what one can do, and I will just stop here, but I just want to tease you a little bit. So what one can do is again look at the general correlation function, and using dual unitarity, one can again reduce a general correlation function, can show it that should vanish. Because of these sideways fusion rules, it should vanish unless the operators are placed exactly on the light ray. But now the operators are in principle two-body operators, so they have to be two-body. I mean, the correlation function between single-body operators is 0. The correlation function is a two-body correlation function. Okay, end of this. So let me just spend the last, I guess, 5 minutes or so on perturbed dual unitary circuits. So now you might say, okay, I mean, this is very particular because you ask a very strong property, but the question is, also integrability is a very strong fine-tuning, right? So now the question is, I mean, can this physics of these models have a chance to be structurally stable? And here I was kind of heuristically motivated by results which I knew from let's say, chaos theory of classical chaos, where people have proven results on stability of hyperbolic systems, classical hyperbolic systems, perturbative stability, and these problems are typically structurally stable. So the question is, I mean, do these models, which are kind of proven ergodic now, but they are isolated points in parameter space, are they kind of structurally stable? And can we prove that? And here we basically started a little program along this line and proved a very modest result, which I will now describe in 2 or 3 slides before I close. So now imagine now you take a general correlation function, again, in the folded circuit representation between operator A and B. So this would be like a correlation function between operator at site Y and operator B at site Y plus X at time t later. And this is like a contraction of, this is like intersection of two forward and backward light cones. So it's basically contraction of this rectangular circuit partition function, right? But it has non-trivial boundary conditions. These operators A and B enter through boundary conditions. Now, this is, of course, becomes trivial as soon as the operator is dual unitary. So in this operator language, sorry, no. In this operator language, this dual unitarity can be phrased in this way. This is unitarity now in operator folded circuit language. And you see, unitarity now is just unitality in this operator circuit representation. And dual unitarity is just dual unitality, which means that when you take two bullets, which represent trace or identity operator from the sides, they just contract. Now, this only holds for gates which are plotted in yellow, which are the dual unitary gates. So now imagine you have a perturbed situation where you perturb every once in a while a gate and you take it non-dual unitary. So now imagine that you have this sort of strategy of doing perturbation theory of taking a small low density of gates which are slightly or strongly non-unitary. Or you can think of density 1 of gates which are non-unitary but with a small strength eta, where P is some Hermitian operator. So this gate U eta is a perturbed dual unitary gate with small perturbation eta. And basically what we can show under various, because probably I will not have time to go into any detail, but the upshot will be that we are able under some simple conditions in some very restricted context to show a kind of a path integral formula for correlation function, saying that when you have these perturbations as kind of impurities, then this partition function, this correlation function, which is a hard to evaluate object, can be written exactly as a sum of all possible paths from beginning to the end, which goes via one-dimensional paths, and the contribution of each path is like a 1D transfer matrix. But paths can get kind of, can change direction on the impurities, on the gates which are perturbed. And of course, this is still very hard problem. So we simplify this problem in a, again, restricted context. In the so-called, we define the so-called reduced gates, meaning that we basically introduce random fields in z direction and we average over random fields. So we make noise which has particular direction. So doing this let's say U1 averaging. So we take a U1 noise and we average over it. Doing the U1 averaging over two-body correlator, we get a correlator of a classical Markov circuit. So basically, we basically immediately see that the only non-vanishing correlation functions are among diagonal operators. And among diagonal operators, the operator circuit is written in terms of a two-side gates rather than four-side. I mean, in general, for qubits, you have 4 operators on each side, but now the only non-trivial operators you have to worry about are the identity and the sigma z. So it's just two states per side. So the two-side gate is just a 4x4 matrix now, and written in this, if you want, Hadamard basis. This is just a classical bistochastic Markov matrix, which is Hadamard transformed. That means that it has one eigenvalue and zeros in the first and the second, in the first row and the first column, and the only non-vanishing elements are these 9 elements here in this block. And now, if you want this matrix to be dual unitary, in this case, after reduction, dual bistochastic, meaning that it's also bistochastic when you reshuffle space and time, then these two guys have to be 0. So the condition for dual bistochasticity is do epsilon is equal to 0. And then, again, I have no time to show you, but there is a very nice representation of correlation function in this representation in terms of tilings of the rectangles, right? So you take T by L, or now, yeah, I mean, depending on the X and T, I mean, this is X plus T times X minus T rectangle. And now computing the correlation function is basically sum over all possible allowed tilings, where each tile basically gives you the weight in the bistochastic matrix. And the kind of nice thing is that if you take these two weights to 0, which means that you take dual bistochastic Markov chain, Markov circuit, then you don't allow the turns. The tiles which have turns, which are the epsilons, are these guys, right? So it basically means that you don't allow the turns. So if you take a perturbative expansion in epsilon, it's basically perturbation theory in the number of terms in this diagram. And now basically what we want to do is we want to make precise statement on under what condition this diagram is equal to the sum over what we call the skeleton diagrams, which are the no loop diagrams. So we want to say, we want to understand under what condition the contribution of the loops is exponentially small in X and T. So I think I have to close, so I don't have time to go into that, but I just want to advertise this is something that has been done in the PRX that I quoted earlier. But then there is a simple theorem which we prove that depending on the parameters of the dual bistochastic gate, there is a criterion which is easy to satisfy, but it's kind of, there is a kind of phase transition. Either you satisfy or don't satisfy the criterion. If you satisfy the criterion, which means that this A, B, C, D, E, F have to satisfy these two inequalities, then the certain transfer matrix has a gap, meaning that the contribution of loop diagrams is exponentially small, meaning that the correlation function can be expressed in terms of path integral form, which is like a many body physics can be expressed in terms like of a one body physics. Okay, I think I have to stop. So I'll just give you my conclusions. So I'll present some exact results on spectral statistics of extended quantum lattice systems when thermodynamic limit is taken first. So that's an important part. All the results that we can do is provided we can take thermodynamic limit first, which limits us to in what we can really say. But then, of course, I believe, provided the first sort of rigorous results. So, for example, we can show the random matrix ramp of the spectral form factor. And also we can characterize spatial temporal correlation functions of extended quantum systems and establish exactly regimes of exact ergodic and mixing dynamics. And we have, in a very restricted context, the first result on structural stability to perturbations of this type of models. The main challenges for future work, I think the main challenge is to try to overcome the restriction of thermodynamic limit taken first, which would be allowing us to make finite size corrections or claims about finite size systems. And that would be absolutely crucial if one wants to make some sort of rigorous claims about ETH. For example, it would be great to be able to prove ETH for dual unitary circuits, but all the tools that we have at hand basically fail. And then the last thing is that, for example, one can make the fully dissipative version of dual unitary circuits with bistochastic crowd circuits, and everything that I told you about correlation functions goes through. And with that, I would like to thank and close.
Okay, so thank you, Thomas. Please unmute yourself and upload the speaker. Okay, so we have some minutes for some questions. We are a bit late. So if you have any question, please unmute yourself and start speaking.
Thomas, can I ask a question? Do you hear me? Yeah. I was wondering, I mean, I hope I understand you correctly. I mean, you take the thermodynamic limit in order to push the Heisenberg time to infinity in some manner of speaking. Is that correct?
Yes.
Okay. Now, in your unitary circuits, you are then left with, at least if you consider the form factor, with this kind of sliding symmetry of John's-Torque, which gives us this linear and T correlations. And I was wondering if you ever tried to look at observables where, well, what in periodic orbit theory would be considered higher order encounters play a role, like, I don't know, I mean, form factor for orthogonal class or some other observables. Is it possible to get them under control in your systems, such correlations?
In dual unitary systems, no, I don't think it's beyond. But there was a periodic orbit-like approach which we had in 2018 in PRX with two students, Pavel and another PhD student at the time. And there we could actually address the second order, let's say, the so-called Richter-Sieber.
Yeah, exactly. Yeah,
because there we did not need to take thermodynamic limit. But this was the model of long range. I mean, this was long range. I mean, this was like a power load decaying, interacting Kick-Dissent model. So we needed to have long range interactions in order to be able to do some sort of random phase approximation. Then everything, then the corresponding, then the problem reduced to a one-dimensional Stackman problem. So it's just time. Now there was no space anymore. It was just time. So the orbits were kind of much simpler. I mean, they kind of factored to kind of, I mean, it's hard to capture things in words in 1 minute, but there you could get your, I mean, familiar concepts from semi-classics, even though nothing is semi-classical because H bar is one. But here, I mean, this is, to me, I mean, you see, I mean, also the mathematics that we use to prove results is completely different than in semi-classics, right? I mean, so
okay, thanks, Thomas.
Any other question?
Maybe I
one question. Okay.
Please go.
Alicia? Yeah.
Hi. So I was wondering, so you showed at some point this hierarchy of chaos, this classification that you find in the dual unitary models. I was wondering if and how this relates to conventional notions of, say, integrability of conservation laws or this thing. For example, if the model is conventionally integrable, does this how does this classify in your hierarchy?
Right. Well, if the model is integrable, you expect to have local conserved quantities, and local conserved quantities would immediately imply that this. Well, I mean, the object that I showed you, which is the object which only characterizes the decay of single particle correlators, this will not see you. I mean, this will only see conserved operators which are supported on single site.
Mm-hmm.
So, I mean, you could say even for integrable systems, if I don't have single site conserved quantities, but I have three site conserved quantities and over, and two site and three site and so on, this object will not see that. So there will be no eigenvalue at one. So
it will appear as ergodic essentially.
It will appear as ergodic, but you could easily take two site and three site and four site observers. I mean, this construction in terms of these transfer matrices, I mean, this can be trivially extended to R site observers.
Mm-hmm.
You just have to, grow things. I mean, grow the wires, the thicker wires, and so on. I mean,
and then you possibly have you may have a different classification.
Eventually, after some number of steps of thickening the circuit, you will get eigenvalue 1 appearing, which will indicate integrability. So integrability will necessarily mean that there will be local operators which will not decay.
I see. Thank you.
Marco, did you have a question?
Maybe very, very quick question, since you were talking about observables. Could you also get things like the out-of-time order correlator of these circuits to understand whether the saturate the bounds or what is scrambling?
I mean, I can just point you the paper by Lorenzo Piroli and Bruno Bertini. They had a paper.
Okay.
Without 2020 on that, exactly.
I just have a very quick question about this perturbation that you explained. Can you say something about the spectrum form factor with that? I mean, how the spectrum of the dual transfer matrix will be perturbed by these gates that you insert?
Yes, that's the second level question. Yeah, so I would love to, but we started with this kind of simplest question, which is what happens to the correlation function. But the next question, which is I think even more pending, is what happens to spectral form factor, because that's easier to connect to maybe issues like localization and ergodicity.
Yep.
So, but that's the next level question. We are thinking about it, but we have nothing.
Okay, so let's thank again the speaker. And let's move on.